Hey everyone, good afternoon. My name is George. With me is Alina and Chee, and we are very excited to tell you more about drive-by compromise. Over the past few months, we bought over 20 dash cameras to check whether they are insecure or secure. And we distilled some of our findings into an attack technique we call the drive-by compromise, which is a literal wordplay on drive-by downloads, where we first compromise vulnerable dash cameras, infect them with C2 scripts, and then tap on their mobility to form a roaming botnet on wheels. As shown above are the 5 stages of infection propagation, and I will be going through them later, especially stages 2 to 5. Let me share with you how we built a mini botnet in our lab environment. But first, some orientation matters. If you take a look at the screen, on the top left-hand corner shows the botnet manager, the dashboard. On the top right shows the scripts that are running at the background, so we know what's going on. Bottom right corner shows the attacker Kali Pai on the red Lego and the first victim on the orange Lego. And on the bottom left hand shows the logical diagram of the soon-to-be botnet architecture. So our attacker is in physical proximity with the first target, which is a ThinkWare F800 Pro dash cam. For starters, it's just connecting to the dash camera with default credentials and accessing the unprotected RTSP stream and then dumping out all the video files through Telnet. Next, we move on to our second to fifth infection stages, where we will upload a C2 script onto the dashcam for it to beacon back to pull new instructions to execute. For instance, finding nearby dash cameras to connect to. Just as I speak, a second dashcam drives by and is picked up by the first dashcam. The first dashcam recognizes this as an iRoot F-X2 model based on the SSID and connects to it. Most iRoad devices, dashcams, they have fixed passwords and they do not allow any password change from the default password. Although the FX2 does not expose Telnet or SSH, we found an unauthenticated HTTP upload endpoint. And so we uploaded a CGI-based web shell and were able to execute remote convictions, remote commands. For instance, we can perform sabotage by disabling the car battery protection to drain the car battery overnight. We also uploaded a C2 script that makes the FX2 scan its surroundings for the next target to infect. For one dashcam to connect another, it must switch roles, going from access point mode to station mode and then back to access point. For instance, we use the WPA subroutine file preferably in the dashcam itself, so we leave off the LAN to connect to another camera. We categorize the dash cameras into 3 levels, and starting from the top, at level 3, we have LTE dash cameras. These are cloud-based dash cameras that rely that has 4G or 5G based cameras connection. That relies on either the phone's internet connectivity, or the car's connectivity, or even the garage's connectivity. Or it could have its own dashcam slot. And then second level, we have CLI-based dashcams. These are cameras that expose Telnet or SSH either directly or indirectly. And level 1, we have the regular dash cameras, where it exposes HTTP, FTP, RTSP, and these are what we call the down cameras. The propagation factor decreases as we move from level 3 to level 1. And as you can see above, on the top left hand, we have just initiated a Wi-Fi scan and we found our next target, which is the Hikvision D1. For our third dashcam, the Hikvision D1, we found its Telnet password on the firmware that was available on the manufacturer's website. Like this one on the ThinkWare dashcam is now attempting to connect to the Hikvision dashcam. And once connected, as you can see on the top left, we can verify its IP address. We can then inject C2 script for it to discover and infect the next target, which will be the 70Mi X200 dashcam, which you will see in a bit. It's worth mentioning here that there is indeed a limitation where instructions and responses have to be cached through intermediary dashcams in order to reach botnet masters, because these are after all local devices. But that changes when we're talking about LTE dash cams. So let's take a look at the 70 My X200 Omni dash cam, which comes with its own SIM card. Once the 70 My dash cam is connected with the C2 script, we can enumerate for GPS data, video files, audio files, and the dashboard above shows the process of us exfiltrating all the sensitive media using the dashcam's FTP put utility from the dashcam itself to our Botnet server. The C2 beacons are also exchanged directly from the Botnet server to our dashcam because the 70 My X200 has internet connectivity. Another dashcam drives by, great. This time a 70 My M300. Many dashcams like this will require a device pairing process such as a 2FA on top of the regular Wi-Fi authentication. The white frame in the middle shows the device pairing process, without which the official 70 My mobile app cannot access the feeds. But it's interesting because we found that this limitation only exists on the mobile app itself. In other words, we could connect to this dashcam's network without pairing the mobile pairing to the official app and access the HTTP web server to download the video feeds. And that is what we are doing over here, exfiltrate video recordings through the unprotected HTTP route through the X200 dashcam, which offers internet connectivity. On the same camera, its telnet password is exposed on the etc password and shadow files on its web server. And because this camera has a weak network stack, we are able to crash it using a single script. Effectively, we have the ability to disable it from remotely. As you can see, the light changes from green to blue to red. What makes this worse is that this model has a unit battery and no way to restart it. There's no reset button. So the owner will have to wait for the battery to drain before being able to turn it back on. And that will take about an hour or more, depending on battery life. And now, the last camera, the iDrive i11. This dashcam's Wi-Fi password cannot be changed, so it relies on device pairing as main authentication. When the mobile app sends a pairing device to this dashcam, the owner will have to physically press the Wi-Fi button on the dashcam to unlock it temporarily for pairing. The dashcam will then remember the MAC address of the user's phone and stores it. So in our attack, we first join the dashcam's network using the fixed password. And then we perform an ARP scan to find out the trusted device MAC address, which is usually the owner's phone, and we spoof it, thereby presenting ourselves as the trusted device. To show what's going on under the hood, we ran the script separately on this Kali Pi to bypass layer 2 device pairing and exfiltrate the video recordings. A quick summary of the conditions required for propagation. First of all, the dashcams are required to switch from AP mode to station mode and then back to AP mode. Do be careful with this step because in our testing we have rigged 4 devices and we've only managed to revive 1. Next, in order for the C2 to ping back, it requires internet connectivity, or otherwise you will have to piggyback on a nearby dashcam. And third, the cameras require sufficient time and within proximity to allow data to exchange with one another. And lastly, the C2 scripts have to be model specific because the weaknesses and configurations vary from models to models. And today we have about 20 plus of them in our arsenal. So what do we do with the sensitive video recordings that we have done? How do we keep persistence across inputs? Chee, can you show us?
Yeah, sure. Okay, so now suppose we have an infected camera that has been infected by our botnet. So as most cameras do not have an external battery power connected to it because vehicles are expensive. So so we actually we have to make sure that the cameras actually is being powered on 24/7 for our persistence knowledge. But if in the case where there's no persistence, like there's no power, when the camera is being powered off every time the vehicle is being turned on, we need to ensure that our scripts actually loads every time the camera moves. So in this case, so in order for new cameras for our botnet to effect new cameras, we need to make sure that our scripts actually reloads every time it actually powers down. So for processors to make to happen. Yeah. So what happens whenever a camera restarts? The camera, like most other dash embedded devices, starts by throwing in elite configurations such as elite tag or scripts to run the necessary processes. After the elite script is being loaded, such as the elite tag over here, RCS scripts, application scripts such as the web servers are being loaded. So the first method to achieve persistence is by hooking onto the application scripts. In this case, we start off by getting access into the dashcam through exposed telnet or SSH, or even by throwing a web shell to get a reverse shell in order to access our dashcam's root. Thereafter, we notice that the cameras actually runs the scripts run go ahead sh. So it actually loads these scripts every time the dashcam boots up. So for our botnet to maintain this persistence, we can actually input our scripts over here such that it will be loaded every time the dashcam is being powered on. However, such a method has its limitation because not all cameras are dumb because manufacturers are smart. They actually mount all these application scripts in the read-only overlay. So in this case, changes only goes to the RAM, not on the flash itself. So every time whenever we power down the dash cam and restart it, all our changes made on the application scripts will be lost. So we need a secondary method to establish persistence, which is to hook onto its binary scripts to go further and deeper such that we are able to make sure that our scripts persist every time the dashcam is being powered on. So the second method will be to hook onto the binary scripts is more riskier because it involves modifying the core system component in this case. So in this example, we notice that our dashcam actually loads the files from S00 all the way to S99 whenever the dashcam boots. And interestingly, for S50, we actually found this function run ISP daemon. And more importantly, ISP daemon does not exist in the user read folder. So to establish persistence, we can actually write our botnet scripts over in this folder and leave it as ISP daemon for the camera to actually boot up every time it loads. But do note that because the camera actually looks from file S00, S1, S2 all the way up to S99, it has to follow an ascending order. So if you want to, give the manufacturer more money, you can actually trick it by, putting your file, running a file loop, an endless file loop, such that the camera goes into a loop always. Yeah, so this is how you get persistence. So after giving persistence to the camera, we want to be able to download the information from the camera itself to understand what the driver is driving to, gain more insights for the driver. So in this case, we will process the video in the following way. So for the videos, we extract the video frame with the timestamps using a Python video processing scripts. Next, when there's a road signs inside the video frame, we actually try to use machine learning to predict if the sign is a road sign because it's blurry, there's different resolutions being created. So we will use machine learning to detect that this is actually a road signs and to identify them. So after identifying the road signs, we will apply OCR using Google calculations to extract the text. And finally, we can, because of the resolution, some of the text extracted might not be accurate. So we need to have more intelligence speed. In this case, we actually run through an ML such as OpenAI to guess the location and to even get a lat and longitude in order for us to plot this route onto Google Map to understand where the driver has actually traveled to. So for the audio itself, we first use Shazam to identify the audios in our background music. So next, in parallel, we will use OpenAI Whisper for transcription. So in this case, if there is any background source of music identified by Shazam, we actually will use AI to intelligently remove whatever songs that has been discovered, all the lyrics, all that, so as to get an accurate representation of the transcription. And finally, we summarize all these conversations into insights using OpenAI, and we try to generate an AI comic in a cute form so as to make it more engaging. And this is how our dashboard looks like. In the bottom left, you can see the source, city, branches of light being identified, which London. Then you can see the background where the driver had traveled to. So in this case, the driver had traveled in the west region of Singapore. So you can also see overall insights from the conversations. So in this case, there's things like confidential discussion being discussed, mentions of all the partnerships, all that, and we actually summarize all this into a cute AI comic over here. Yeah, so to make it more engaging. So now, Alina, can you tell us more about the trust levels for connected vehicles?
So thanks, Chee. So now we come with the considerations that we need to look for in expanded attack surfaces for the connected vehicle ecosystem. So as vehicles become increasingly connected, the attack surface expands across several fronts. So firstly, 5G mobile apps and cloud services now intertwine with safety critical systems and increasing cross-flow risk. Secondly, consumer apps and cloud APIs can leak or expose access points if not hardened properly. Thirdly, insecure telemetry or over-the-air update channels may breach backend systems within vehicle networks. Fourthly, weak LTE authentication or dash cameras or telematics can actually enable lateral movement. And finally, when data and control planes like telemetry or CAN or UDS comes together, without proper isolation, it will create even more attack surface areas. So it further condense the attack surfaces and exploitation paths into 4 different attack surfaces. So firstly, for external vectors, such as the 5G kits and telematics, misconfigured APNs or static credentials in firmware will also result in further lateral movement. Also, weak TLS validation can also result in man-in-the-middle or token theft. So for internet track vectors, such as your infotainment system, having unsegmented networks will actually allow easier lateral movement, such as CAN bridging, or even having outdated SDKs or libraries and debug interfaces that are not synced properly will also result in further compromise. So next, we have vectors concerning the mobile applications in cloud. So privileged escalation via the mobile app and the cloud to telematics can be possible due to API key leakage. So if there is any missing CMAC or even signing packages, the OTA update chains can be possible, can be made insecure as well in this case. So for dash and cloud recorders, exposed HTTP endpoints and outdated libraries can create a potential vulnerability point as well. So after describing all the threat models, where does safety becomes surveillance? So the privacy impact over here for cloud storage is for continuous uploads that actually use weak or static tokens. These APIs can actually link live video feeds, GPS data, and also driver profiles, effectively enabling remote surveillance. So misconfigured buckets or TLS validation flaws expose footage to the internet as well. And also for drive recording and telemetry correlation, such as your embedded GPS data, your timestamps, and the speeds can be cross-referenced with public data sets. So even though we have like anonymous data, but these can be traced, de-anonymized, or traced back to the public using your license plate matching or route tracking. Next, we have mobile app integrations where if your app stores and credentials are verified and SSIDs are used insecurely, these can allow token reuse and remote data of local ID access. And then last but not least, from data attack surfaces, you have your aggregated footage that enables tracking and profiling, and cloud dashboards created distributed surveillance networks. So the attackers can actually use these paths as reconnaissance for lateral movement. So to discuss all the threat vectors in details, these are your recommended hardening strategies. So for cloud dash and cloud services, enforce NTLS, encrypt stored media, and rotate your tokens. And for infotainment systems, make sure that you segment your CAN networks and disable any unused debug ports. And for mobile apps, apply signing and cert healing. Do not store API keys on the client side. So for fleet management systems or backend systems, implement monitoring and secure the update chain via CMAC or package signing to ensure firmware integrity. So last but not least, allow users to perform telemetry opt-outs and privacy control using the
Peter, this is the conference.
so
You are exceeding your time limit.
over to you, Celine.
Hi, guys. Hey,
Bye.